In 1913, Cambridge University was the undisputed center of global mathematics. Its halls were filled with the brightest, most rigorously trained academics in the world, including a highly respected 35-year-old fellow named G.H. Hardy. Then, a strange letter arrived on his desk. It was from a 23-year-old clerk working at a port trust office in Madras, India. The young man wrote that he was poor, had dropped out of college, and possessed zero formal university training. Yet attached to this introduction were 9 pages packed with highly advanced, alien-looking equations. In one section, the clerk made an impossible claim. If you add up all natural numbers to infinity, the sum equals -1/12. Most baffling of all, the pages contained absolutely zero proof to explain how he arrived at these answers. In the rigid world of Western academia, mathematical proof is everything. You cannot simply state a correct answer. You have to document the grueling, step-by-step logic required to reach it. Without proofs, Hardy's immediate reaction was to dismiss the entire letter as a hoax. But the equations lingered in his mind. Hardy brought the pages to his colleague, John Littlewood, and the 2 leading mathematicians of their generation spent hours analyzing the clerk's work. By midnight, they reached a startling conclusion. The math was so incredibly advanced, it had to be true. As Hardy later put it, no human being possessed the imagination to simply invent them. The Cambridge establishment was suddenly forced to confront a raw, unexplainable intellect, one that arrived at their most complex results while ignoring every rule of the academic process. That intellect belonged to Srinivasa Ramanujan. His world in South India was the exact opposite of Cambridge. His family was exceptionally poor, surviving by taking in subtenants to afford basic necessities. They were strict Vaishnavite Brahmins, members of the highest caste in Hindu society, living a life heavily restricted by ancient religious rules and deep isolation. Ramanujan's mathematical origin story didn't involve elite professors or prestigious libraries. At age 16, he acquired an outdated textbook written by a mathematician named Carr. It was essentially a cram book containing 5,000 equations and theorems with almost no explanations. Without step-by-step proofs to study, Ramanujan treated every equation as a raw puzzle, training his brain to find the solutions through pure intuition. He also operated on a unique philosophical framework. Ramanujan was deeply devout and credited his genius entirely to his family's goddess, Namagiri. He did not view mathematics as a human construct. To him, these equations were the literal, unalterable thoughts of God, downloaded directly into his mind. When Hardy invited Ramanujan to Cambridge, those deep religious roots initially stood in the way. As a devout Brahmin, crossing the ocean meant risking excommunication from his caste and his community. He was trapped in India until his mother had a vivid dream. She saw her son surrounded by Europeans and heard the voice of the goddess Nagamari, commanding her not to block the boy's destiny. With that divine permission, Ramanujan boarded a ship to Europe. By growing up in a total academic vacuum, Ramanujan avoided the slow, linear training of Western mathematics. He didn't need the ladders of proof. His mind simply operated at the destination. In 1914, Ramanujan arrived at Cambridge. He was a fluid, intuitive thinker, dropped directly into the rigid, stone architecture of British academia. The friction was immediate. Hardy stepped in as Ramanujan's editor, determined to publish his friend's discoveries. But Hardy required rigorous proof. Day after day, he desperately tried to force Ramanujan to document the linear steps behind his answers, while Ramanujan struggled to explain formulas he claimed to just magically know. His processing speed was baffling. Once, Hardy visited Ramanujan in a cab and casually mentioned the taxi's number, 1729, calling it a rather dull figure. Ramanujan corrected him instantly. He identified 1729 as the smallest number that can be expressed as the sum of 2 cubes in 2 different ways. Without missing a beat, his mind had perfectly mapped the intersections of cubic numbers, a number multiplied by itself 3 times. To see the true gap between standard mathematics and Ramanujan's intuition, take a look at this chart tracking the calculation of pi. Because pi has infinite non-repeating digits, traditional formulas, like the one developed by Gottfried Leibniz, require an immense amount of calculation. As we plot the Leibniz formula on this graph, you can see the line bouncing erratically. You would have to calculate millions of terms along the x-axis just to slowly inch toward a few accurate decimal places of pi on the y-axis. Now, watch what happens when we overlay Ramanujan's custom formula on this exact same chart. With just a single calculated term, Ramanujan's equation plots a point directly on the true value of pi. It correctly calculates 8 perfect digits instantly, entirely bypassing the chaotic process required by traditional mathematics. Standard academia relied on an agonizing staircase of logic to prove a concept. Ramanujan's intuition allowed him to see the final result long before anyone else had even begun the first step. Just as Ramanujan was finding his rhythm in England, World War I broke out. The collaborative intellectual haven of Cambridge was emptied out, heavily militarized, and transformed into a harsh, depleted landscape. The shift took a devastating toll on Ramanujan's body. He was trapped in the freezing English climate, a weather system his body had never experienced. He strictly adhered to his Brahmin dietary rules, requiring meals prepared by specific standards, but wartime rationing made ingredients incredibly scarce. Soon, he was surviving on little more than rice, salt, and lemon juice. Severe malnourishment set in. Combined with total cultural isolation, the stress of Hardy's academic demands, and a mysterious illness, widely suspected to be tuberculosis, Ramanujan's mental state shattered. He reached his absolute breaking point in the gloom of a London underground station. Severely depressed, Ramanujan threw himself directly in front of an approaching train. He only survived because a sharp-eyed guard managed to pull the emergency switch, halting the massive machine just feet from his body. The same intense, quiet isolation that fostered his unique perspective in India became his undoing in a rigid, foreign environment. After the suicide attempt, Hardy made a desperate push to validate his friend's work. He wielded his academic influence to secure Ramanujan a fellowship at the prestigious Royal Society. It was one of the highest honors in science, previously held by men like Isaac Newton, and it represented the ultimate acceptance of Ramanujan's methods by the very establishment that once required rigid proofs. But the recognition came too late to save his health. Ramanujan returned to India a physically broken man. Even as he wasted away in constant pain, he spent his final, feverish days churning out strange new mathematical ideas he called Mach theta functions. 4 days before his death at the age of 32, he was still scribbling equations. For decades, nobody fully understood what those final equations meant. Today, a century later, physicists use Ramanujan's Mach theta functions to help understand the behavior of black holes and the dimensions of string theory, concepts that did not even exist during his lifetime. Human progress relies on systematic, logical steps. But mapping the physical universe occasionally requires a singular mind willing to skip the staircase entirely and take a leap of absolute faith.